Hi guys, this is Dr. Gonzalez here, and in this video I'm going to walk you through how we conduct an independent samples t-test. You should have watched the first video, which is where we went over one sample, and in this particular video we're going to go over independent samples, and this is where we compare the means of two populations. So what a t-test does in the independent samples version is it compares the means of two or more independent groups, and we're looking to determine statistical significance. And that statistical evidence is going to be that those association population means are going to be significantly different. That's what we're testing. So you've got an image down here that kind of summarizes what we're doing. We've got two population distributions down here, right? We've sampled from those populations. We've done something different between the two groups. We have a sample mean for each of them, and we're going to compare them to see if there's a significant difference between them. So there's a lot of different names that are used for independent samples t-test. It can also be called an independent t-test, an independent measures t-test, independent two-sample t-test, student t-test, again, two-sample t-test, uncorrelated scores t-test, unpaired t-test, unrelated t-test. But all of those things mean the same thing, independent samples t-test. And what that breaks down to is that the variables in this test are going to be a dependent variable for your test variable, and you're looking at an independent variable that is our grouping variable. So when do we use it? We use this test to look for statistically significant differences between the means of two groups, of two interventions, or the means of two change scores. And big thing you need to realize is that an independent samples t-test can only compare the means for two and only two groups. If you've got three groups or four groups, there's a problem, because when we start looking at that pooled variance across all of those different groups, it actually gets harder for us to have our significant difference to show there in an easy way, right? So when we go into ANOVA, I will break this down and show you what I mean. But for now, just understand that if you've got two or more groups, you can't do a t-test and you'll have to do an ANOVA. And that's why we cover ANOVA in this course. So your data for a independent samples t-test, they have to be continuous. So that means they have to be measured with an interval or a ratio scale. You're going to have an independent variable that's categorical, so that means treatment or no treatment, and it's going to have exactly two categories. If I've got more than two categories, I'm moving on up to an ANOVA. Now, your independent samples and groups have to be there. You have to have independence of observations, and what that means is that there's no relationship between the subjects in each sample. So in other words, I've got group 1, and the subjects in group 1 are only in group 1. They cannot also be in group 2. And it also means that if a subject is in group 1 and it might influence a subject in group 2, this would not be the right place to do that either. And the group itself can't influence the other group. So that's what we mean by independence of observations and independence between those groups there too. We also need random sampling of the data by either selection or assignment. We need normal distribution for that DV in each group. We need homogeneity of variance, and we need no outliers. And in this particular walkthrough in Jamovi, I'm going to show you how we check for homogeneity of variance. So we didn't do that in the last example video, but in this one, since we're dealing with two groups, we need to make sure that those groups have homogeneity of variance. So there's a rule of thumb when it comes to independent samples t-tests. Each group needs at least 6 subjects. Ideally, you need more than 6. If you fall below 6, what happens is when you make an inference for that population, it's going to be tenuous, and it may not be a true representation of what you would want in order to run this particular analysis. You also need a balanced design. So that means you need to have more or less the same number of subjects in each group. So obviously, if I only had 6 subjects as a minimum, and I had 6 in one and 10 in another, that would be kind of, we need to go and check and make sure that we're not violating any homogeneity of variance with that. The larger your group sizes get, the more reliable your outcome is going to be, because that increases the probability that your standard deviation, any variation that you see in that group, is actually close to what you would see in the population. So for our independent samples t-test, we can have our hypotheses represented in two different ways. Both of these different ways, you've got mu1 and mu2, and those are your population means for group 1 and group 2 respectively. Okay, so I can have one way of setting it up right here. I can say my null hypothesis is that mu1 equals mu2, and what that says is that my two population means are equal. Or I can say down here the same thing, just in a different way. I'm saying that mu1 minus mu2 equals 0. So that means that the difference between the populations is equal to 0. In other words, there's no difference, because if your difference is 0, then there's no difference, right? Then for our alternative hypothesis, we say mu is not equal to mu2. Okay, obviously that is simply a two-tailed test. It's just telling me my two population means are not equal. Or I could also say that the difference of mu1 minus mu2 is not equal to 0. So that means there's a difference between those two means, and it's been determined to be statistically significant based on whatever p-value that we have established. Now, those all on this page right here, these are all two-tailed, okay? If I change these around and used a greater than or a less than, then I'm switching to a one-tailed situation, okay? Now, one of the assumptions that you had to meet for an independent samples t-test is the assumption that you have homogeneity of variance. And what that means is that both groups have a very similar variance. And the way we want to check that is by running a test called the Levene's test. And a Levene's test even has its own hypotheses, right? So what we're looking at is variance. So we have a null for our Levene's test, and that null says that the population variance for group 1 minus the population variance for group 2 is equal to 0. That means that they are equal because we do want homogeneity, right? And then we have an alternative that says the population variance of group 1 minus the population variance of group 2 is not equal to 0. Not equal to 0, that means that our groups are not equal when it comes to variance. So if your variances are not equal, you have violated the assumption of homogeneity of variance. And you're going to need to go do a different statistic other than an independent samples t-test. So let's see how this would look when you run it in Jamovi. So when we go to check for equal variances, we're going to have to select an option in Jamovi that's going to test for homogeneity of variance. So when you pull up your t-test menu, you're going to see an assumption check right here. You're going to see homogeneity test. So that's what we're going to do before we get into the actual real deal here. We're going to go do that first. But let's talk about the actual calculation that's going on behind the scene. So when we're doing an independent samples t-test, what we are saying is that our two independent samples were assumed to be drawn from populations that had identical population variances. So population variance of the first one equals the population variance of the second one. And so as long as that's true, our test statistic would be computed this way. So this should be familiar to you because it talks about our pooled standard deviation, our pooled variance that we talked about in the previous videos. So T is equal to the mean of the first sample minus the mean of the second sample. And remember, in the other video, this was written as M1 minus M2, okay? And that is divided by the pooled standard deviation, which is the square root of 1 over your n sub 1, which is your sample size, plus 1 over n sub 2, which is your sample size for the second sample. And then we calculate that pooled variance down here by taking our degrees of freedom. This was df in the other video, degrees of freedom, plus the degrees of freedom here, divided by n sub 1 plus n sub 2, and this time we are subtracting 2, so those are our degrees of freedom, and we get the square root of that. Remember, this is what's going on behind the scenes in Jamovi. We're not going to do this by hand, but we did need to understand, remember, the components of the particular formula so that we can understand conceptually what's going on. Now, in an independent samples t-test, our calculated t-value is going to be compared to a critical value for t, just like we did in that one sample. We're going to get that from our t distribution table, but this time our degrees of freedom is going to be n1 plus n2 divided by 2, because we've got to adjust that because 2 of our possibilities have been taken up by the mean now. And we're going to look at that degrees of freedom plus our chosen confidence level, which is going to probably be 0.05 because that's usually what we go with. And that confidence level is also our P, right? So your calculated t-value is going to be greater than your critical. We're going to reject the null hypothesis if it's a one-tailed situation, which is what the scenario is here that we're going to run. We're assuming equal variances, but we're going to check that. And because we assume those equal variances, it is okay to pool that sample variance like we talked about when we calculated this by hand. If you violated that, your pooled variance would not be accurate, and that would affect the accuracy of your t-statistic and consequently also your p-value. So whenever you have two independent samples that are assumed to be drawn from populations with unequal variances, your test statistic is computed a little bit differently, okay? You see here you've got a little bit of variation in that formula. We're going to take that variance, instead of using pooled variance, we're going to use this formula down here to get our degrees of freedom, which is going to go back into that formula. But again, this is all the math behind the scenes, and we're not going to worry about that at the moment because I would rather you understand the formula we went over in the other video. I just want you to see that there's a difference between this formula and that formula. So this is when our variances are the same, and this is when our variances are not. We have violated homogeneity of variance, so we use this formula. All right, so how would your data need to be set up? Your data needs to have two variables. You're going to represent those in columns. The independent variable is going to be a categorical variable, and it only has two levels or two groups because that's all we can handle in a t-test, right? Your DV, though, is going to be continuous, which means it has to either be interval or ratio. And the number of rows in your data set is going to correspond to the number of subjects in your study. So each row of the data set is a unique unit, and all of the measurements taken on that unit have to be in that row. So this is what it would look like. We're going to go back over here to Jamovi. Make sure if you had closed Jamovi, make sure you open it back up. We can go over here to data. Actually, you can move that out of the way for now. This is what it looks like. We don't need this participant variable. It's just there because we've already used those two variables in our previous study. So now you can look and you can see that under electronics group right here, which is what we're going to be doing an analysis on in a moment, I've got two different levels. I can either have electronics as usual or no electronics. That gets an intervention. And then I'm going to have some data on, again, we're doing sleep duration. So I have Apple Watch duration, in the IS stands for independent samples because that's what we're doing here. And then the PSYC quality independent samples. Okay. Let's go back to our presentation. So here is the particular study that we're going to run, or the little experiment that you're going to run in your data here. So Dr. G wants to test if electronics used before bed affects sleep duration and quality. We're really just looking at duration. That's the only one I looked at, I believe. Participants are adults. They sleep at least 5 hours per night, and they don't have a diagnosed sleep disorder. Participants are randomly assigned. Remember, that's important for an experiment. To one of two groups. They either go into the treatment group, which avoids all electronics for 60 minutes before bed, or they go into a control group, where they're allowed to use any electronic, what they would normally use is what we're looking at. And they're going to collect data on their sleep over a month. That Apple Watch data is going to give us a mean sleep duration for a month. And also at the end of the month, they're going to answer the PSYC, and we're going to pull that sleep quality and sleep duration data from it to get our means. So data on sleep duration were from the Apple Watch. After 1 month, participants also completed their PSYC, and they got an overall sleep quality score and a subjective sleep duration. Our research question was, does a no electronics before bed intervention affect sleep outcomes compared to typical electronics used before bed? So we've got 2 groups, right? One that's going to be allowed to use electronics, one that does whatever they want to do instead of electronics. This is our intervention group down here. A month goes by, they collect data with their Apple Watch. We also give them the PSYC at the end, and we see what happens. So let's look at our hypotheses. These are going to be one-tailed because we're only looking to see if, I think I did it one-tailed. No, I did it 2. I apologize. I did it 2-tailed. So I said my null is that there's no difference in average Apple Watch sleep duration between adults in the no electronics group and adults in the electronics group as usual. Then I have an alternative that said there was a difference. I did not indicate a particular direction so that you could see how that looks in Jamovi. Okay, so my alternative is that there was a difference. I don't know if it went one way, if it went the other way. I could also write this down here using less words. I can say the mu of no electronics was equal to the mu of the electronics group. And my alternative is that the mu of the no electronics group is not equal to the mu of the electronics group. So this would be my intervention, and this would be my control. I could have used that instead of these words. It would have meant the same thing. I also have a set of hypotheses here for my sleep quality. Okay, I did do quality. I thought I did duration, but I did quality with the Apple Watch and duration with the PSYC. So I said that for the null that there was no difference in PSYC, there was no difference in their sleep quality. For the alternative, I said that there was a difference. And then I wrote that down here using mu again. So mu of no electronics was equal to the mu of electronics. And the alternative is that the mu of no electronics was equal to the mu of electronics. Okay, remember this is quality. The other one was duration. All right, so let's figure out what our critical values would be. Now remember, this is something that you're not going to see in Jamovi, okay? So you would pull up that t-test table, and I believe, let's see what it looks like in Canvas here. So you'll see what I mean. So when you go into Canvas and you look at I don't want to take a survey. You go down here to t-test and you see this, the t distribution. You click on that and you're going to see a PDF. Maybe. There you go. You see this PDF. This PDF came from the Graviter and Wall New Book. But you'll notice one of the issues with this particular distribution is that as you get into the degrees of freedom, everything is great until you get up to the larger numbers, right? It cuts off, which is why whenever I give you this chart to use, I will definitely make sure the problem falls into the degrees of freedom that's shown on here. If we go back to my presentation, I've actually cut the table from a different place, and I actually cut out the portion that showed what I needed to show you. So if you remember, I said that the degrees of freedom is n minus 2. So in this particular situation, n would have been 51 in each group, 51 participants. So 51 plus 51 is 102. So now when I subtract 2 from it, I get 100, which you could easily see on the chart. That's why I kind of gave you a situation here where the numbers are very specific. So if I use that, I am looking at my degrees of freedom of 100. So I would follow this over. And my probability this time is still 0.05, but I'm looking at 2 tails. So I would come over from that to right here for my 0.05, go down, and then 1.984 is going to be our critical value. So our critical value is plus or minus 1.984. So that means our corresponding p-value from there is going to be less than 0.05. So what does that look like on the distribution? Here's what it looks like. So look at the image here. This time I've got 2 shaded regions under the curve because this is 2-tailed, right? I'm looking at an alpha level of 0.05 with degrees of freedom of 100, and that gives me my critical values of plus and minus 1.984. So negative 1.984 is over here, and positive 1.984 is over there. So if I get a value that falls underneath this tail right here, then I would reject the null. If I get a value that fell under this area of the curve right here, I would also reject the null. And I'm going to fail to reject it if my t-value falls between negative 1.984 and positive 1.984. Okay? And then we're gonna reject it if it's less than negative 1.984 or if it's more than 1.984, and that corresponds to a p-level of 0.05. And then we fail to reject if negative, if it falls in between, if our t-value is between those 2 critically bounded areas. So how do we run this? What we're going to do is we're going to go over here to our data set, and you're going to go to Analyses, t-test, and this time we're going to go to Independent Samples. So go back to the PowerPoint presentation, Analyses, t-test, Independent Samples. And what we're going to do is we're going to move electronics grouping to our electronics group to grouping variable, and you're going to move Apple Watch duration, IS, and PSYC quality, IS, to the dependent variables. Okay. I know these variables are worded kind of strangely, but that IS stands for independent samples. So what I mean is instead of giving you 3 different databases to work with, I put all the data in one. So we did our 1 sample earlier. Now we're moving over to our data for the 2 sample, which is going to be our grouping variable, the Apple Watch duration, and the PSYC quality. All right, so let's go back to Analyses, t-test, Independent Samples. We're going to take that electronics grouping variable and move it over, and then we're going to take our Apple Watch duration and put it in dependent, and we're going to take the PSYC quality and put it in dependent. So let's talk about what we need to mark down here. So make sure you've selected all of your appropriate options. So this time we were testing a 2-tailed hypothesis. So under hypothesis, you're going to select group 1 is not equal to group 2 right here. You're going to stay on your students right there. We're not going to do Welch's or Mann-Whitney U. We're not going to change anything under missing values because there's nothing wrong with these data. Under additional statistics, I want you to click mean difference, effect size, and descriptive so that we have all that we need to write our conclusion up for our data set with regard to APA. So you're going to select mean difference, effect size, and your descriptives. And now this time I told you we were going to check our homogeneity variance. So under assumption checks, I want you to click homogeneity test. And before we look at those outputs, I want to go over what we're doing in that homogeneity of variance test. So what we're doing there is we're testing to make sure that our variances are equal between those two groups. And by equal, I mean equal within a statistical range, right? They don't have to be exactly the same. So what we're going to do is we're going to look at the assumptions output from Jamovi. And from that, we're going to test our hypothesis about the variances. And what we want to see is that our null is true. Okay. So the population variance from group 1 is going to be no different than the population variance of group 2. Or in other words, those variances are equal. Our alternative hypothesis would be that they're not equal. So we're going to look at the p-value for the output of the assumptions test. And what you should see when you have run that, we wanted the mean difference, we wanted effect size, we want descriptives, and we want that homogeneity test. So when we look at the assumptions here, homogeneity of variance test, this is the Levine's test. We see that for Apple Watch duration, we have an F of 1.014 with 1 degree of freedom. Your degrees of freedom 2 here is 100. There's a reason it's 1 and 100. We would report that. You need both of those degrees of freedom if you were going to report the statistic. But our P is 0.316. And for our quality, we see our F was 0.571 with 1 and 100 degrees of freedom, and our P was 0.452. So what that means is because the P's were greater than 0.05, there was no significant difference in our homogeneity of variance. In other words, our variances were equal, and that's what we needed to prove. We have equal variances. We needed to prove that before. I'm so sorry. I wish there was a way that I could use a pen on that. But we needed to prove that homogeneity variance, those equal variances, before we can proceed with the test, or before we can interpret the test, because it did it at the same time. Okay, that's good. That's what we wanted to see. See, can I get rid of those? Because that looks really sad, writing it out like that. I'm going to get rid of it all. Looks so much better now. All right, let me change that back to a laser pointer. All right, so now that we have what we wanted to see there, we can proceed. So we can keep going. So we're going to review our independent samples t-test results for duration first. And if you look at your output, we're looking right here, Apple Watch duration. We did a student's independent samples t-test. We got a statistic of negative 6.81. Degrees of freedom was 100, and our corresponding P is less than 0.001, which is less than 0.05. We had a mean difference of negative 0.735, and we have a Cohen's d of negative 1.35. So let's go back and interpret that. So what are we going to do? We are going to reject our null because our t statistic was negative 6.81. And that is definitely less than our bound, which was negative 1.984. And it's confirmed because our P value is less than 0.005. And that's right here, Apple Watch duration. And there's our Cohen's. We'll talk about that in a minute. Okay, so we're going to reject the null on that one. Now let's look at quality. So we want to see if there's a difference in sleep quality between the group that used electronics before bed and the group that did not. And so what you get was, for quality, we had a statistic that was calculated as 5.94, 100 degrees of freedom, and that 5.94 is definitely greater than 1.984, and so our P is less than 0.05, and actually there's a mistake there. That should see confirmed by P is less than 0.001, because that's where it's coming from right there. Okay, so there was a significant difference in sleep quality between those two groups. And you can see down here, mu electronics as usual, and then mu does not equal to mu of no electronics intervention. So now we're going to have to write our APA format output, and we're going to include our effect size, and we're also going to state first that we verified our homogeneity of variance by running that Levene's test. And based on the results of that test, we can assume homogeneity of variance. And there's all of the output that we need for that. So what we would say is that an independent samples t-test was conducted to determine if average sleep duration differed between the electronics as usual group and the no electronics intervention group. Results showed a statistically significant difference in sleep duration. We report our T first. T of 100 degrees of freedom is equal to negative 6.81. P is less than 0.001, and our D is equal to negative 1.35. Participants in the electronics as usual group slept an average of 5.72 hours per night, and then we report our standard deviation for that mean. It was 0.59. While participants in the no electronics group slept an average of 6.45. So you can see there's a difference, right? You can see 5.72 versus 6.45. It's almost a whole hour. And their standard deviation was 0.50. So the no electronics intervention group slept an average of 0.74 hours longer than the electronics as usual group, and therefore our null hypothesis was rejected. And we'd go back and we would report our Cohen's for that as well. And if you go back to the results, the Cohen's for that first one was a 1.35. It was a negative 1.35. The negative doesn't matter. It's still a significance there, significant effect size. It's a very large effect size. And then we do the same thing for our sleep quality. On the PSYC, what participants do is they get a score, right? And that score, the higher it is, the worse their sleep. So we would say an independent samples t-test was conducted to determine if their sleep quality scores differed. Results indicated a statistically significant difference in PSYC sleep scores between the groups. We say a T of 100 equaled 5.94, P is less than 0.001, and our Cohen's D is equal to 1.18. Participants in the electronics as usual group had a higher average PSYC score. Remember I told you higher means worse sleep, with a mean of 9.06 and a standard deviation of 1.92, and we're comparing that to the mean and standard deviation of the intervention group. They had a score of 6.98 with a standard deviation of 1.59. So the mean difference, where do you get that mean difference from? You get that from your output right here, mean difference, okay? The mean difference between the groups was 2.08 points. Lower PSYC scores indicate better sleep. So these results suggest that participants in the no electronics intervention group reported better quality sleep than participants in the electronics as usual group, which means that our null hypothesis was rejected. Okay, so that is the end of this presentation for the independent samples t-test. I will finish this video and we'll continue with our last example, our paired samples t-test, in the next and final video of the lectures.